A runner accelerates uniformly from rest to a speed of 8 meters per second. The kinetic energy of the runner was determined at 2 meter per second intervals and recorded in the data table below. So the table gives us his speed as it increases and the kinetic energy that he uses in order to accelerate. And we notice that the kinetic energy is increasing disproportionately faster than the speed is increasing, so it takes him more and more energy to keep building speed as he goes faster and faster. So let's see if we can graph this. So why don't we do 2, 4, 6, 8 on the x-axis? Say 2, 4, 6, 8, 0, 2, 4, 6, 8, and this is his speed in meters per second. And then along the y-axis we have the kinetic energy that he uses in joules. And we'll go 500, 1,000, 1,500, 2,000, 2,500. Okay, so this is 2,500, 2,000, 1,000, and 500. Okay, so when he's only going when he's going 0 meters per second, when he's not moving, he doesn't need any energy to do that. So that the origin is on the graph. And when he's going 2 meters per second, it takes 140. So I'm just approximating here. It's about there. And when he's going 4 meters per second, it takes 560. So that's up here. And when he's going 6 meters per second, it takes 1260. That's quite a bit more. Maybe that's up there. And then when he's going 8 meters per second, it takes a lot. It takes almost 20. Maybe that's about there. And now let's see if we can draw this graph. Let me just move that one down a little bit. I think that was a little overzealous. It's only just a touch above 500. Okay, so now if we try this again. So you can see it's this sort of exponential curve. These are just choppy lines, but if I made that like a nice smooth curve, then you'd get an idea that this is an exponential relationship. And so that's it. We plotted the data versus for the energy versus speed, and we sort of drew the line of best fit, right? So it's going to be a nice smooth curve there. So that takes care of 66 and 67. And now they want us to calculate the mass of the runner. Well, what is the equation that describes this relationship that we just graphed? This is really kinetic energy equals 1/2 mv squared. So if we know the kinetic energy that he uses at different velocities, and it always fits on this graph, then we can choose an ordered pair. We can choose one of these points and plug in the energy and plug in the velocity and find the mass. So let's do that. Let's plug in, I don't know, we'll do 1260 and 6. We'll use this one. You can use any one you want. They should come out the same. So if he has 1260 joules, and that's equal to 1/2 his mass, which we don't know yet, times his velocity squared, which is 6 meters per second squared. Then I'm going to just continue down here. So 1260 joules now equals, what is 6 squared? It's 36, right? Divided by 2 is 18. So we'll say 18 meters squared per second squared times his mass, which is what we want to know. So now we'll solve for mass, divide by 18 on both sides. Mass equals 1260 joules divided by 18 meters squared per second squared. And if you put that into your calculator, you will get 70. And now let's just check out the units. A joule is a Newton meter, and a Newton is really a kilogram meter per second squared. So really this is kilogram meters squared per second squared, and that's being divided by meters squared per second squared. So meters squared over meters squared, second squared and second squared, and you end up with kilograms, which is exactly what we want. We want to know the runner's mass. So the runner's mass is 70 kilograms. And again, if you try a different point like 4 and 560, you should be able to verify through the exact same formulation that his mass is 70 kilograms. So that takes care of 68 and 69, and then 70, a soccer player having less mass than the runner also accelerates uniformly from rest to a speed of 8 meters per second, just like this guy, but he's less massive. Compare the kinetic energy of the less massive soccer player to the kinetic energy of the more massive runner when both are traveling at the same speed. Well, clearly, kinetic energy is directly proportional to mass, right? Because this is the formula. So the less massive player is going to need less kinetic energy. But the kinetic energy is proportional to the mass directly, and it's not related to a square. So you could say that the kinetic energy for the smaller player is correspondingly lower in accordance with his relatively smaller mass, right? And again, they're not looking for us to calculate exactly because they haven't given us numbers, but it's sufficient to say that the smaller player uses less kinetic energy due to his smaller mass, and you could say that too. But important just to recognize that because he's lighter, he requires less kinetic energy to accelerate up to 8 meters per second like the runner. And that's all.